Client-side prediction in Nengi is pretty complicated. It's conceptually simple. All you're trying to do is move, in the browser, and then move in the server. We do this by collecting commands on the client, like WASD, arrow keys, the mouse, whatever it is for that game. We save them as a command, then we send them to the server, and also before they've been processed by the server, we run them locally and move ourselves. That is, in essence, the prediction, this idea that we're going to predict locally what the server is going to tell us in the near future about what the result of these commands were. You can see here in the simulator, the actual line that matters is this line here with move command, where it sends the state of WASD, it sends a rotation, and it sends the delta of the frame. What does that mean? What's the significance of that? Well, sending the delta of the frame gives us a deterministic amount of movement. If our movement logic is something like go in, up, down, left, right, by our speed times delta, that is an equation that can be run on the server and client to the same result. This is very important for prediction code because prediction code relies on this determinism, else the client will predict something different than what the server did, and when the client finally hears back from the server, there's going to be some very harsh rubber banding. Keeping things deterministic is a matter of thinking about whether an equation can be repeated on server and client to the same result. This one of the delta is a good example of one that can. Another good example is if you press W once, then on this client move up one, and then send it to the server, and then when the server hears W, it moves you up one. That would also be deterministic. An example of something that's not going to come out the same on the two would be, for example, I started pressing W. Then on the client, you start moving up, and then at some point you release W, you need to say to the server, I stopped pressing W. And then the server hears you started, it starts moving you, and then it hears you stopped, and it stops moving you. Why isn't that deterministic? Well, that one's reliant entirely upon some sort of implication about time. It's never actually says how far you moved. What if the server lags? What if the client lags? One of them might hear about W having been pressed for a different amount of time. Not to mention that they're spinning at different tick rates. So little errors in physics can accrue, not errors so much as deviations, on quite a few equations, especially if they're complicated at all, when they're run at different tick rates. This is solved by having logic that is very focused around delta time. This whole concept of delta time in games and determinism in general is covered at length on the internet if you'd like to read more about it, which I highly recommend if you ever try and predict any kind of sophisticated behaviors. So let's take a quick look at a game with prediction running. Let's see, let's go to localhost. I've got the game running locally, or I could Google something about lerp rotations. Okay, so here I'm localhost. My movement feels instantaneous. We're talking about the movement of the prediction of movement here. Feels like I'm playing a single player game. To be fair, this was never a candidate for something that was going to have a problem. I'm playing from localhost and my server's running on localhost. There's really no latency between these two. Let's go to the internet because I've got the same demo running on a server in New York and I'm in Seattle, so that should have some latency. Here it is. I'm going to reconnect, make sure this is actually still up. Yep, it is. So I'm playing in New York. Feels the exact same as if I was playing locally. I'm living the prediction dream. Let's throw a nightmare at this dream. I'm going to use this packet filtering program. I'm going to add 250 milliseconds of latency to all outbound packets. I'm going to reconnect. You can actually see the lag on the reconnection. It's even affecting the page load. Now I'm playing the game. Feels the same. Truly the prediction dream. This demo also has prediction of shots, which is not going to be covered in detail in this particular video. I'll talk about it more later, but it does help here to exhibit how much lag we're showing. Here, white is the predicted shot. It's come out instantly upon clicking. Red is the shot from the server. This is, not something you actually show in a game. This is what we're actually trying to conceal. But for the sake of this demo, it's a good debug tool. You can see how much white and red are deviating from each other, and thus how much lag I really am experiencing, even though my movement feels smooth. So that's what it looks like. That's the thing we love. Going back to the complexity of the code a little bit. How does it work? Talked about using the deltas. Talked about making sure things stay deterministic. Those are all requirements of it to get it to work. But the actual implementation is a little more complicated than that. And we are aided a little bit by nengi. So nengi sends snapshots from server to client every frame. These snapshots are just the game state, that frame. And the client works in a similar way, where anytime you're sending commands from client to server, it follows a very similar model where it makes snapshots of those and sends them. You can in fact send more than one command from client to server. For example, this game in particular always sends a movement command literally every frame. But when you click the mouse, it also sends a fire command. So on that particular frame, that snapshot contains both a movement command and a fire command. The snapshots sent from client to server are stamped with a number. This is all inside of the core of nengi. You don't ever have to worry about it. And when the server sends a snapshot back to our client, it returns to us a number, once again, deep in the core of nengi, that represents the last set of our inputs that were processed by the server and thus are reflected in the state of the world as of us having received the snapshot. This means that nengi, specifically the client, is aware of how many commands we've sent to the server that have yet to be processed or reflected in the game state. This is accessed in nengi via client get unconfirmed commands right down here. Anything returned from here is a command that we've pressed, we've sent to the server, but the server has yet to respond to us and say that it's heard about it. This is one half of the data needed for us to form a valid prediction. The other part of the data needed is we must know where we were on the server as of the last thing it confirmed. Now, that might sound like, okay, well, isn't that just whatever we just got out of the interpolator? Because that's, the data we're getting from the server. We now know what commands we've sent that haven't reached it, and we've just got the state of our game. But the interpolator has a bit of a delay on it. And because of that, it's not actually the freshest state. It's 100 milliseconds old. And prediction is a very touchy thing. You really want your latest state. So to accomplish this, on the game server, I in fact send to the client its last authoritative X and Y in a message. What's special about that? Well, messages in nengi are not interpolated. There's nothing to interpolate. A message is a single fire event. There's no concept of A then B, let's interpolate between them. Messages is, hey, this happened right now. Every frame, we send this. So this is the other piece of the data. We know which commands we've sent to the server that haven't been processed, and we know the last known authoritative position for our character. These come together in predictor.js to actually do the prediction. This bit of code here at the beginning where we reset our local copy of our entity to the last authoritative position, that's that authoritative position that was sent. If you read the rest of the code, you'll see how it gets piped through. And then this command set right here is that command set that came from the commands that have yet to be confirmed by the server. So every frame, to perform the prediction of movement, we snap ourselves to the last known authoritative position, and then we run the movement code, the identical movement code from the server, taking in these commands. This creates our smooth movement. Conceptually, it's, conceptually, it's a bit of a challenge. Or implementation-wise, it's a bit of a challenge. There's a lot of moving parts. And there's also nuance to it when we get into other topics, such as firing, because predicting a shot doesn't work that way. We wouldn't want to fire the gun every frame until we hear that the server said we fired the gun. That's not the correct result. The next video we'll talk about firing, prediction, and some more of the nuances of prediction.